My name is Daniel, and I'm coming from Ergon. And today I want to talk about spatial computing. It's a new wording, and you might not be familiar with it, but it's upcoming. And in the end, I'm here to a bit raise the awareness and show you what all your work also, and what the work from all the universities around the world and ETH precisely, is contributing to this new era of computing we're currently facing. First of all, on the agenda is I want to show you what spatial computing is. So we're going to talk shortly about the naming. Then I will show you 5 key aspects which are necessary that we can go into this space. And then I would, don't want to talk about theory. I will show you our example, what we did in the last couple of months. I will also show you the pitfalls, because not everything was solved, but we're software engineers, so that's why we're here. We're going to solve it. I will show you a short demo that it's not going to be too long, and in the end, we're going to sum it up. Spatial computing is in the line of all the stuff you already know. Personal computing, mobile computing with the upcoming smartphones. And now we're going into space. So the English pronunciation for that is just spatial. The desktop computer from the 80s, even though the new one might look different, it looks different, but the concept is the very same. You have a 2D screen, you have a keyboard, you have a mouse, and everything what you want to do on your PC is you have to sit down either on the table or maybe it's a laptop you can carry, but it's all bound to this 2D screen, what you're interfering with. Mobile computing on the other side, in the beginning of the 2000s, when everybody suddenly had a smartphone, we were able to carry that stuff and bring it with us. So now it's, for example, it's a lot easier if you say, I want to take a tram to the main station. You have your mobile, and you don't have to type in where you currently are, because the mobile knows where you are and can show you a nice timetable and even give you guidance where the next tram station is. Spatial computing now takes this 2D screen and that 2D screen and just erases it. So instead of we're using for example, glasses, AR glasses, like the one from HoloLens. This is the first model, or the new one. And when you're at ETH, you will know that, because ETH is actively working together with Microsoft to create those. All the optics, or a lot of the optics, is coming from Zurich. And you might be even involved in that. I envy you, to be honest. So the screen might now float somewhere in space. This is a virtual screen, which I just recorded from outside and took a screenshot of that. So the worker now has hands-free, doesn't have to carry something, and the information now is bound to somewhere in space. I promised you 5 key aspects. Those I will talk about today is scenic understanding. Then we need to have some data. We need to store the data somewhere and distribute it. We need to have some visualization. In this topic, it's AR. And we need to be able to localize the model that we can match them perfectly. Scenic understanding, and I promised you in the notes that I will compare all the different type technologies, how they contribute to the spatial environment. We need to have a lot of machine learning here, and we need to have a lot of optics, which are able to recognize the physical world, recognize where is a plane, maybe a horizontal plane, maybe a vertical plane, and then also classify those planes. It might be a wall, it might be a door, it might be a window, or it might be an object like a table, and all these are, in the meantime, built into the OS. So if you have a modern Apple or Google phone, that's already bound into the basic foundation we have. Then you have different machine learning algorithms to, for example, detect moving objects like people and segment them from the foreground and the background, that we can use them to augment other stuff or other virtual stuff. So we need to have some way to understand our surrounding. Then we need to have data we want to visualize. The saying for that would be a digital twin. And when I was searching for a nice picture for my slide, I stumbled over ETH again. So you're everywhere. You can create a digital twin of a building or a simple object. You can create a digital twin of, for example, sensors, a sensor network, or in case of ETH, you're going big, and again, the whole world. To simulate stuff, to simulate atmospheric changes, to simulate flowing of the liquids around the globe, and you have to have a virtual representation. Then you need to have some data layer, how to distribute that. There are some walled gardens from Microsoft, from Niantic, for example. They're using they're piggybacking Pokemon Go to collect all the video and the measurements of certain spots around the city, crowdsourced by all the players. Microsoft is providing a service for geolocated services. And this example would be from Magic Leap, so to be honest, the only competitor to that one right now. And it's like a 2D map, what you're used to right now, Google Maps, Apple Maps, but it's a 3-dimensional map of the whole world. And so you need to have a geolocation of every element, and then you can, on top of that mesh of the volumes, you can add some semantic layers, which are then used for specific use cases like construction, like city planning, or just leisure. The augmented reality we're talking about is just the front end. It's like, yeah, it's Angular for space. It's fine. You can use it, you can display your stuff, but it's all 3-dimensional, and we just need to have some way to visualize the content. So either it's those waveframes in the display, or it could be your smartphone, your iPad. It's capable of doing that, and you all carry it with you. And that's why we, as in a consumer market, we're focusing right now on the smartphone and tablet-based AR, because everybody has that, and hardly anybody carries this around. It is, well, you have it's useful for certain aspects, but when you have to go to a certain corner, boot it up, there's Windows running on that, so it takes a while. You just take your smartphone, and this is just a lot faster. And the first approach, which is currently live and capable of really running in production. And the last point is, as I said, we need to match those two models, the virtual world and the physical world, to be able to have the same representation. Again, you have some ways to do that. You can scan certain landmarks, you can scan certain images if you know the position. Outdoor is one topic. Indoor is a lot harder, because most of the time you need to be a lot more precise, and you don't have that many sensors. GPS indoors is sometimes hard, and it's also not accurate enough. Google just announced that the airport in Zurich is the very first location where they have a publicly available indoor navigation, which is purely based on those images and the scenery they pre-scanned at the airport. Again, this is now publicly available. 2 years ago, Google made the very same project together with SBB for Zurich main station, but that just ran out. So now Google is providing that service to the public. Those are the things which need to come together to be able to provide a service which is running in space. And as I said, I don't want to be too boring, so I want to show you something which we really did. And in our case, this is coming from construction work. And I will discuss those 5 aspects now, shortly. First thing is a BIM. I don't know if you're familiar with that. BIM is short for Building Information Modeling. So architects nowadays, instead of building a small paper model of the building, they create it in 3D, and they are able to discuss a lot easier. And before starting the build, they already have a full-blown model of the new building. Especially in large buildings like airports and hospitals and bureau and industry, this is common in the meantime. It will become a necessity even. But it's not just the walls and floors and ceiling and the model, but it also contains all the piping. So you can simulate already an airflow in the airport before doing the build. That saves a lot of time, and people get used to that. And we took that, and you saw the image already, put that in an AR application on the iPhone, on the iPad, that you're able to, while working, just have the model with you. So it's not bound anymore to your office and the expensive rendering machine with a RTX 3090, but it's bound to the iPad. I will show you a short video how that looks like. This is the basement of a retailer, and so we loaded the model. You have a small mini-map like in games, and you can walk through the building and have a reference of the. You see those small white parts. This is the virtual model, which is just highlighted because we're looking at it. And suddenly you have a lot more options for constructing, for avoiding errors, and or fixing stuff. So back to those 5 things. We need to understand the scenery. This is basic. This is even free. You can start doing that today, and there are amazing tutorials from all the big players, Microsoft, Google, Apple, to detect the planes, to detect the meshes, so the volumetric objects here, and then doing this SLAM algorithm, so simultaneously, while you're walking through the scenery, it updates the map and localizes yourself. We have the data, because architects already did that. There are people spending hours and days and months building the virtual model, so we use that for free. We have AR, because it is bound since years into our smartphones. And, well, for data storage, we did build an application, so our backend is our data storage. We can access it from as we want. The last part, the localization, the mapping of those 2 models, it was just not there. Well, there are ways to localize yourself, but for our needs, it was just not there. But we're all engineers, so what are we doing? We created our own. Okay. We created our own solution, which works in the construction site. And I will show you also that in a short live demo. What you do is to localize yourself. On the map, you just mark, like in Google Maps, here I am. And then in AR, you just confirm the assumption. So, the demo. Perfect. Not sure how far I can walk. So, I would be on the construction site. The model is already loaded on the iPad, so there might be no Wi-Fi, there might be no cellular, so I cannot download the model on site. I pre-loaded it in the office, and you just have to come with me in this mind game now. We're in St. Gallen in the hospital, because I don't have the model of ETH. If you have, I'm really interested. But well, so it does not match this particular building now, but I can still show you the approach we're following. First of all, I'm selecting the floor where I am. This would be the floor where I am really, and now I have a map of the hospital in St. Gallen. And well, you might even know the visuals. I'm marking my position. That would be the position where I'm really at. So, and okay, yeah. That's all I have to do. I have to mark a rough estimation of where I am. And the next step is, this is really short, I'm scanning the same scenery which I just said I'm really at. And that's it. Now I'm done. The localization is done, and I can load the model. Unfortunately, your corner here is not 90 degrees, and mine in the object is, so that's why the corner here is not, looks wrong. But if you see, it's bound to that initial point, and this is my anchor where I can load all the object. I can, well, display everything. This is quite a lot. And now I can walk. This is 6 degrees of freedom, so I can really move around in this scenery if the cable is long enough. I can also blend in the current scenery. So now there should be a wall right here, but I can't walk there. But I have a really fast way to compare my model with the real work somebody built. People can even consult the model before starting the build and might do something wrong. And this is exactly what we're doing. And you have all the, I need to switch that off. And you have all the piping now again. Not the real ones from here, but now you can have an X-ray into the model. So much for the short demo. Good. And presenter. There you go. Yeah. Of course, we're quite proud of that solution. We also patented it, so I have to tell you about the benefits and why it makes a difference. But that's if you're working on machine learning, if you're working on new ways to distribute data, to store data in the cloud, on the edge, or to process data in the edge and do all this really fast transmitting of data. I just want to give you a concept you might have in your back mind that you know for what you're doing that. In our case, the construction work, well, after I showed you that short demo, I'm pretty sure all of you can do it. If you're a gamer or not, if you're familiar with minimaps or not, this is really an easy way to implement it. It's quite cheap because we don't need anybody to 3D scan the whole building. 3D scan is outdated anyway because people are building the building, so next day there might be a new wall, which is missing in my model. There is no sensor network, there is no indoor navigation. We tried all that, but in the end we ruled it out because it's not a feasible option for the construction site. It's maintenance free because there's no hardware. You can upload the new model and then you can go again. We don't need any connectivity. It's all happening on the iPad. It's on your smartphone, so everybody can use it, not just those having the 3,500 franc AR glasses. And the model is layered, so you can adapt it to whatever you want to see. So if it's the piping or if it's just the walls, for example. And because you're here at ETH, I have to tell you it's a mathematically approach. So we do calculate where this corner is and how we can match it. It's not an assumption, it's not an estimation. So it's really precise in the end. So what we're doing in the end is we have these volumetric models. We detect the front-facing planes, do edge detection, cut it in a corner, and then match it against those things we get from the machine learning approach from the real world. We can do with that, well, we don't have to discuss about the correct way of doing things. We can just look at the same picture and it's really intuitive, it's really useful. We can have a cool X-ray into things. For example, this fridge, if it's broken, you can have an X-ray and see where the piping is and where you can start fixing it. And of course, in our case, documentation and quality assurance, this is exactly the use case we're implementing. So when somebody is on the construction site and is using our model, you mark something, one specific object, and then in our application, we have a small little dot exactly in our backend, and now you can go back to work and tell people, okay, here's an error, here you have a screenshot, you have a reference to your BIM model, and it's amazingly fast and really useful. So to sum it up, spatial computing, this is one example now, but spatial computing is a new way how we think about use cases. It's not mobile first anymore. It might be, this is what IoT started a long time ago, but we bound stuff to the sensors, to the actors, and we can write software which is just living at a certain space, and when we pass by, we can access it if we have the rights to do so. And those examples I showed you now they are just the beginning. This is really the 20s will come, those will get cheaper, and the frameworks will get better, and you will create a lot more machine learning stuff, which will be integrated in the front ends. And then you can go even further. The interaction with the system can get quite wild. You can track the eyes. Those have cameras which are turned back, and they can see where you're looking at, and so you don't need your hands anymore to interact with software. You can look at the lights and switch it off by a blink. We can, by understanding the situation and by understanding the surrounding, we can even try to find out what's the current intention of the user, and then give some specific guidance for the next steps. And this is, for example, while you're working, you don't need to have documentation about the goods, but we can really scroll to the documentation. Very last point, and this is not something we can drop. The data we're handling there is new, is more precise, and is critical, because the kind of data is shifting. We have a good discussion about which data is private and which data is in social networks, and how people are using that. But the data we have in AI applications is the next level. The kind of data, for example, could be quite sensitive. When you're carrying a camera with you all the time, but go to the bathroom, you don't want it to be switched on. You might not even be allowed to record certain people or places or confidential information, but the AR glasses might do that for you and still compute it in the edge or in the cloud, so somebody else's computer. And we need to be aware how to deal with those. There are certain risks because the data is real-time data. It's not something you actively choose that you submit. If you upload a picture in social media, this is your consent. This is your decision that you upload this specific picture. But if you have a running video, you share with the world, you share with the owner of the application, you share with the backend, you might contribute your data to somebody else. And there are some limitations, and you need to be aware. What we found out in those early stages, and there is a lot of discussion going on about these privacy issues here, is we're taking the privacy into consideration from the get-go of the project. It's not something, so we call it privacy by design. It's a common concept also for other applications, but this is a must for those, because you cannot implement something which is technically possible and feasible, but in the end, discuss how to keep your data private. Our approach right now is to be brutally transparent of what's happening. As I said, all the data of what we just had is staying on this iPad. There is nothing transferred to anybody, and this transparency is not just for the software developers, but for the whole stack. So the end user need to be aware what they're doing, what they're allowed to do. The software developers, the hardware developers, and sometimes you have walled gardens, so you have no idea what they're doing with the video stream or with the spatial data. But also the application owners need to be really transparent what they're using, how they're monetizing the stuff, whose data is it? Is it the one who's collecting the data or the one providing the data? And to really come to a conclusion is, right now it's the best way to have this informed consent of the user, because in the end it's a lot about your personal data and your friends, your bystanders, you're recording. So the user is the one really being able to have an impact here. So instead of giving you terms and conditions, nobody reads, you just click the checkbox and continue at the first time when installing it. We really need to have this informed consent. So you give the consent to a specific use case, to a specific solution for the next 5 minutes. Am I allowed to use the camera image to scan a QR code for the next 5 minutes? Could be a simple question, and this is starting in the mobile sector, where you have those capabilities you need to tick as a developer, and I think this is going in a good direction, that we really have a better limitation on that. And in the end, we're back in gaming. It might be a tutorial you start, and in the beginning you just get a very limited set of features you can do, and after passing those, you get some perks, and you can do a bit more stuff. So you really need to understand what they're doing. And yes. So thanks for that. We can discuss a lot. If you know, I'm from Ergon, we have a big booth downstairs. If you did not come, please consider. And we have a virtual reality flying simulation, which is quite fun. So if you want to try it out, come by. We will be at the booth, but that's the not interesting stuff. Maybe. If you have any questions, if you want to discuss something, I'm happy.
I'll pass around the microphone for the ones who have a question. Just raise your hand if you have any questions.
So how do you estimate the impact of this technology? Is it something that will replace what we have now, like mobile computing and personal computing, or will it be a complement, like mobile computing is to personal computing at the moment?
My personal opinion is it's a complement, yes. It's like your mobile. PCs did not go anywhere. They're useful for certain things. You still want to have a keyboard sometimes because it is easier. Yes, there are speech to text implementations in the meantime, but still having a written version where you can make up your mind will not go anywhere. The big screens will not go anywhere. So for the next couple of decades, it will be a complement.
How do you really assess the impact that it might have? Because in my opinion, for example, the Google navigation in the airport, like it can help, but I don't really see that it helps that much. Like, yeah, normally people don't get lost at the airport, or if they do, they like spend 2 minutes for doing that.
Those early adoptions are always really a bit handmade. When I'm in a city where I'm not familiar with, this AR navigation is quite useful because you can go out of the subway, take out your phone, and don't have the problem that you're walking 180 degrees in the wrong direction. So sometimes it's useful, yes, but the big thing is how fast and easy is it to get to that information. So when glasses are getting smaller, it might be the glass because you just wear it, and then you walk from one certain digital content to the next one, and if you have access to that, you might get that content in a specific role if you subscribe to that, for example. But right now it's more in a B2B content or gaming. Gaming is always a factor because it's for fun. But the current impact I see is more in business context.
Yeah. So my question is with regards to, for example, when you have, the iPad in front of you, you're on the construction site and you're looking at a pole and the pole is in the wrong position. Yeah. How do you kind of assure the user that it's not because it's not because the software is not like incorrectly calibrated, but it's really that pole was constructed in the incorrect position, for example?
We're starting at a specific point. that's what we're visualizing with those cones. So this is the reference point right now. This is not geolocated somewhere at a specific GPS coordinate and direction, for example, by the way. This is the big difference between having to have the correct visualization, you need to also be aware of the rotation. This is the critical part, to be honest. Yes, it could be that the reality differs from the model. But if it's, first of all, the information that it differs is already something they need to discuss then, because it might stabilize the whole building or impact the stabilization of the whole building, and then they need to redo their math. So in the end, right now, they are mainly, if there is a difference, then they are taking the picture and taking it back to the model and do the measure. But at least you have a visual representation that there might be a difference, because right now you cannot tell. You can't measure all the Abstände, distances. Thanks. From any object. So if you have a corner in the corner of a room, that's quite stable. And at least those pillars also, they are the first things they build in the large buildings. And when you reference it to one pillar, you can be sure that this is correct. And if something else differs, you need to go back to the model.
Just another quick question. And what kind of drift do you experience when you're walking, for example, from one end of the hospital to the other? Do you then have to recalibrate, or is it really quite accurate?
We're running on the newest models with LiDAR, and there is no drift. It's different to Google phones because they differ so much. But on the Apple devices, it's really stable. I tell people that they can restart it anytime, and they do after a couple of tries. But first thing is when they see it, they walk 20 minutes through the whole building and are amazed. Yeah, I did that then. And so it is stable, but it's not meant to be used for 20 minutes straight, to be honest, because you're there to build stuff or to control stuff or to review, and not to walk through your model.
To follow up, so did I understand correctly that if the user exhibits drift for whatever reason, then the current model is to restart, recalibrate, and go on again?
You will experience drift when we lose access to the camera and the IMU. So that's why we force the whole AR visualization to cancel and destroy the whole AR visualization when the app is going to background or when something else is happening. So when we lose the confidence that you might turn off the screen and just put it in your backpack and then take it back, then you need to redo it again. But that's why our approach is that this has to be really fast and anywhere, that you can just restart it. Thanks for coming. I'm really pleased that so many people listened to that. If you have any more questions, I'm at the booth, so thanks.